It's my pleasure to introduce the first speaker of today, Professor Shlosman, and his talk is about Tracy-Widom distribution, Ising model, and many related fields. Please meet Professor Shlosman.
Thank you for the invitation, and I am happy to talk on the conference dedicated to Vadim Alexandrovich MALYSHEV. He was he made a very big impression on me for many years. His versatility in subjects that he was interested in. He was very active in pursuing some new perspectives, and I was very envious hearing from him that he currently was changing his field of research, and many projects that he undertook during his scientific life. Outside this, he was also an outstanding musician. For example, I was living at his apartment in Paris, and he introduced me into some pieces of music which I never knew before, and in his interpretation I learned them for the first time, which I vividly remember. He was always very careful to have a piano at his apartment, and he was playing, maybe even upsetting his neighbors, but he was unable to go without it. So he was a dear friend, and it's very sad that he passed away due to this this COVID virus he got. This is a room he spent many hours teaching and listening to seminars, so it's very appropriate to have the conference here in the university. So my topic is on the screen. It is about KPZ scaling and the Tracy-Widom distribution in the Ising model. So I am very happy to talk about this, because I was working on the Ising model for many years, and I was also always thinking that maybe it is not so advanced as other topics in mathematical physics, where you see some very strange scalings and not only Gaussian behavior. And now it is clear that the Ising model has ground to exhibit all this fascinating behavior also. So so what I will talk about is So this is a picture which is so what I will talk about is a rough caricature of what you see on that screen. Mainly the topic would mainly concern the picture that you see on the bottom left figure, where you see a crystal of lead, and you see there several layers, several monolayers, which are smaller and smaller as you go upward. And what I will talk about is about the top layer and the behavior of the fluctuations of this top layer when there are many layers below it. So it is those, it will be the fluctuations of this object that I want to discuss, and I will try to convince you that it is there, that one can see Tracy-Widom distribution, but this is just a picture to have it in mind, and now I will go down and I remind you about the Ising model a little bit, which is those are photos of the crystal. So this is a very small lead crystal. Yeah, there are many pictures like that.
Isotopes, different numbers. 100, 111. Are those different numbers for isotopes?
No. This, I believe, this is the notations from the crystallography theory, different axes of the crystal. No. It's lead. I don't think lead. I think lead does lead. Lead doesn't have isotopes. At least I don't know about them. So the Ising model is something which is well known in this room, I hope. So we have lattice. We will talk about three-dimensional lattice to begin with, and we have spins ±1 sitting on the vertices of that lattice. And to every configuration, we assign the energy HV of sigma V. Sigma V is collection of spins in the finite box V, and we take a sum of products sigma X times sigma Y. Sum is taken over all bonds in V. X to middle Y means that X and Y are nearest neighbors. And then from this, we make a probability distribution. Mu of sigma V, the probability of seeing sigma V, is proportional to the exponent of minus beta times the energy of the configuration sigma V. And we normalize this Z is a normalization factor, which makes this, the right-hand side, a probability distribution over the set of all sigma V's, all configurations in the finite box V. To make things more interesting, we do a little trick. We put some boundary condition outside V. That is, we fix some configuration sigma bar outside, and we count in the energy of sigma V, not only the interaction inside the box sigma V, but also the interaction of spins in the box V and the spins outside this box. And but then again we normalize, then again we have a little bit different energy. This is the energy of configuration sigma V with respect to the bound, to the configuration sigma bar outside V. And again we write very similar expression for the probability distribution on the configurations sigma V in the finite box V. In particular, we can take two different boundary conditions, two different configurations sigma bar. One is all pluses, the other one is all minuses. And then using each of those, we get a probability distribution. One will be denoted by mu plus, and the other one would be denoted by mu minus. So still, those two are again probability distributions on configurations in the box V. And the nice feature of the Ising model is that when we take the box V, when we take the box V to infinity, those two probability distribution mu plus corresponding to the plus boundary condition and mu minus corresponding to the minus boundary condition, those two have limits, and the nice feature, the prominent feature of the Ising model is that there is phase transition there, which is manifested by the fact that the two probability distribution mu plus and mu minus are sometimes the same and sometimes different. Those two limits are the same for in the high temperature region, that is when beta is less that are equal to some critical value. And once temperature is low enough, once beta, the inverse temperature beta is bigger than the critical temperature, those two probability distributions are different. And this is what makes the Ising model famous for describing the magnetization phase transition, the appearance of magnetization in it. And we will talk about the case when the temperature is low. So beta large, beta bigger than beta critical. Everything is clear, I hope. So if people want to ask questions, you are welcome to ask them right away, not to wait till the end of my talk. Okay, so so we call those two probability distributions, mu plus and mu minus, as plus phase and minus phase. Okay, so they look differently. The plus phase looks like a sea of pluses with small islands of minuses. So this is a plus phase with small islands of minuses, and this is a minus phase, which is sea of minuses with islands of pluses. So those are two phases. This is the minus phase, mu minus, and this is mu plus. Okay, very nice feeling to give a talk and using a blackboard, old-fashioned blackboard. Okay, so the next step we want to do is to create a droplet of one phase in the other phase. So there is a plus phase, there is a minus phase. There is nothing as a phase of pluses mixed with minuses. So in order to do that, we have to go to what is called canonical ensemble. Namely, we start to consider, we take this measure mu minus, but we can restrict it only to the configurations when this magnetization M capital, which is the sum of all spins, is taken to be fixed value. So for here, as you see, I consider this value of magnetization to be a constant times the volume of our box. And for example, if we take this constant m small to be, say, -1/2, then what we will see is that there will be a sea of minuses because we are in the minus phase, but the fraction of pluses would be abnormally high. We will never see this in a typical configuration of the minus phase. To see this, we really have to apply this restriction to this non-typical configuration of our model when we have a very big number of pluses in the sea of the minus phase. So the typical picture would not be what you might imagine. It is not the case that we just have minus phase with many pluses there. No, what will happen is that we will have this minus phase, but those extra pluses would form a large droplet like this. So still there will be some small islands of pluses here, and here will be islands of minuses in this large droplet of plus. But there will be one giant droplet to which all the pluses would combine, like the quicksilver. If you do the small droplets on the table, then the droplets would merge into one single big droplet, and this is the crystal of the plus phase in the minus phase, which we are going to study. Of course, this island would be not something regular as I draw here. Rather, the picture would be like this. So it will be some random surface separating the minus phase from the plus phase. So this is a random two-dimensional surface, and this is what we want to study. Tanya, please.
In terms of dimension,
It is just it's independent of everything. This is just there is nothing special in it. I'm not sticking to that one for just if you put some constant there, then you will have some droplet of the corresponding size. Nothing deep here. So 1/2 is just to make an example. It will be the same if you put some other value, not very close to 0, not very close to 1. Some intermediate value, then it forces a droplet there. Very good. So what about this droplet? We want to be able to say something about this droplet, about the shape of this. It turns out that it has asymptotic shape. If we take, so this is a box n by n by n. And then when we scale it by the factor of n, then we get to the unit cube, unit box. And then this droplet would become something, then we will not see fluctuations. It has some limit shape. So this is a non-random surface in three-dimensional case, or maybe non-random line in two-dimensional case. And this variational problem can be solved. The solution is called Wolf. It is given by the Wolf construction. How to draw this surface? What is the minimal surface which has smallest possible surface energy? This is the solution to that problem. So this droplet has asymptotic shape, and how close the asymptotic shape is to the random surface I am advertising here was studied in two-dimensional case in the book by Roland Abrushin, Roman Kotetsky, and myself. In a three-dimensional case, this was done in papers by Thierry Badinot and independently by Raphael Serf. So one should think about taking this surface here to make the two centers to be nearby, and then want to study the fluctuations which would appear here. What are the fluctuations between this asymptotic shape and this random object? So it is like law of large numbers, so to say. So we have a random object. It has some limiting behavior, and then you subtract the mean value, this limiting behavior, from this random object, and then you study what is the distribution you get there. Very good. So so this is what you see here is the answer for the solution of this variational problem in three-dimensional case. This is a surface. This is a dice, and the surface looks very much like a dice. It has 6 flat facets. This is the artifact of the lattice that the Ising model is defined on. So it has 6 flat facets, and then there are rounded edges and rounded corners. Those are nice smooth surfaces, and there is some singularity at the edges of the facets, And so you should compare this with the first picture I showed you about the lead crystal. So you should think about this as something similar to this lead crystal. And what we want to study is how this surface, how this random surface is behaving, where the flat part stops to be flat and becomes a rounded one. So this crystal, if you go back to the, maybe when I go back there to that picture here. So see again this top, bottom left crystal. It has a flat facet, as you can see here, and then there is some boundary, and we want to study the process, the random process of that boundary, and this facet for me would be the same as the facet of this dice, and we want to see what happens there at the edge of the flat facet. Okay, to see better what goes on there, what we do, we do the following. So we consider still another boundary condition for our Ising model in the three-dimensional case. So we take a three-dimensional cube, and we put, so this is dimension 3, and we put minus boundary condition on the, how is it? Yes, we put minus boundary condition here, and we put plus boundary condition here. So, and then we have the interface here. So we position ourselves on the facet by considering this boundary condition. So you can imagine that we put our box of observation right on a facet, so above facet and below the facet. So you see above, okay, we have one face above this interface and the opposite face below the interface. And then we imagine that we are sitting on the interface, and we want to know how this droplet would evolve as we make the volume of that droplet bigger and bigger. So the bottom line is the following. So we take this boundary condition, pluses on one side, minuses on the other side. We consider the corresponding Gibbs distribution, which is once again given by the same formula, energy of the configuration given this boundary condition. And then we change our canonical constraint. We change how, what is the value of this constant m that we have here. So, and we look at how the picture that we will see will change when we increase this parameter a there. So now I see that I made a wrong picture. We should think about pluses below and minuses above. So, and then we put more and more plus particles into our system. We force the system to have more pluses. So, and then we ask what happens with this interface. So the more pluses we have, the higher the interface should go, right? Because you put more and more plus particles into it, and okay, the interface should go upward, and this is what we want to study. And okay, and then let me tell you what will be the story there. So we did this with late Dima Yofe for several years. We were going back and forth from that project. So there are those 3 papers that we wrote in the course of our studies. And what I'm going to tell you now is a little bit of the 3rd paper, formation of the facets for an effective model of crystal growth. So this crystal growth is what will happen with this probability distribution, this m mu pm, as we vary the canonical constraint, as we change this constraint, m capital is equal to an square, and we change a, and we want to see what will happen with this, with the interface. Okay, so again, this is the same picture I'm telling you about. So we have all classes below the xy plane, all minuses above this xy plane. The plane itself is on is now flat. So the cube is divided into two parts, and if we take this constraint a to be just 0, then the interface is, of course, is just flat, because if a is 0, that means that roughly half of the pluses are pluses. Sorry, half of the spins are pluses, half of the spins are minuses. But this is very consistent with this boundary condition. So we have plus phase below, up the minus phase above the interface. So the interface has no pressure, but just stay flat. So it will be a flat interface between the two phases, okay, with some microscopic fluctuations, but those we are not interested in. We want to see only features of that random interface which are of the size of a system, of a linear size of the system. So we ignore the microscopic fluctuations which are going up and down, which are sitting on that interface, but we don't want to see them. So imagine that we position ourselves on the top of this cube, and we look on the interface, and we record what we will see there. And this is what we will see. You should ignore the cursor there. So we will see just nothing when this parameter a is smaller than some positive value a1. Everything depends on temperature. I will not put this dependence here. So this empty square, what is it again? We sit on the top of that cube, and we look down on this interface, and so we will see the square, the border of that interface is the square, and then we fix all the interesting features of that random surface, which features are of the linear size of the system. And I am saying that when a is less than some a1, then we will see just empty square. So it's an interface with nothing interesting there except microscopic fluctuations, which we ignore. Okay, that is the picture there. And then when we bypass this value a1, then the following picture will be seen. So as a goes above the value a1, then what will happen is that this interface, I'm telling you, cannot stay flat. It cannot absorb all the extra pluses that I force into my system. So what will happen is that this interface is flat, but then it will develop a monolayer of plus spins here. So the extra pluses push this interface up, and the result would be that we have our flat interface, which was initially there, gives up, and there is some monolayer of height 1, which is positioned on this floor of 0 height. So here the height is 1 relative to the xy plane, and inside here the height is, so I'm sorry, I said it wrong. So here the height is 0, and inside this monolayer the height is 1. So one extra monolayer is created there, like the monolayer you saw on that picture, but there it was several of them. But here just one of them would appear, It will be some random line, some pancake, if you wish. And so it is located somewhere in that box. And then let's see what will happen with when we increase this A. So we increase it, and then, okay, this is a bigger value. So the pancake is bigger. It starts touching the walls of our box. We increase it more, then it becomes even bigger. So now it is pressed flat against the walls. And then if we increase it still more, if we bypass the value A2, then what will
Кто-нибудь слышит?
Да, звук у всех пропал.
Да, видимо.
Да.
Окей. Господа, мы ничего не слышим. И картинка не двигается. То есть связь пропала.
Это точно.
Анатолий Дмитриевич, ты слышишь, нет? Он здесь вообще.
А я написала Ивану, сейчас, наверное, переподключится.
Окей. Как раз когда критическое значение А2 достигли, все отключилось. Ну что, Паш, начинай свой доклад для нас.
Да.
Вот, вроде возобновляется все.
Да, Маргарита написала, что пытается исправить проблему.
Павлик, значит, пока нас не слышит.
Окей.
Нет, я слышу.
А понятно, Павлик?
Ну, понятно, да, конечно.
Хорошо. А ты спрашивай, Павлик, если непонятно.
Да, ты продолжай, Сеня.
Сеня.
Давай, Павлик, давай ты будешь контрольный слушатель.
Спасибо, спасибо, спасибо за доверие.
Давай ты будешь контрольный спикер, Сень. Давай.
Да. Может, да.
The heights of the plateau. You said height 1, height 2.
Да, with respect to the coordinate plane.
Exactly 1 and exactly 2.
Exactly 1 and exactly 2. Right. But neglecting the local fluctuations. So there are small fluctuations, but typically this random surface in 90% of the points is at height 0. It coincides with the plane XY. But then there are fluctuations up and down, small one. But 1 and 0 and 2 should be understood literally, except for
So they are very close to the
1 unit. So it is monoatomic layer, like on that picture. So those are layers of thickness 1 atom. Yes, that's how the crystals are made. There are
But the size of the volume
is n large, is n capital. Right?
it is very close to the bottom.
It's close to the middle because my interface is in the middle. I have right. The box is from -n to +n.
Why?
So because of the boundary conditions, my interface is on the
Zero is
in the middle. Yes,
so this is like what?
right. Which picture? This one. This picture. This is for all the pictures. They are from the top, right? And this is from the side. Yes, sure. So we're sitting here. Yes, we're looking down there, and then this pancake is this monolayer, which is we see like this. Okay. So see what happens here. So there are two monolayers. Then when we increase A, the evolution is such that the inner one grows, the outer one shrinks, so they meet. Then what will happen is that both of them are growing and they are very close to each other. And then we bypass the value A3. Oops. And then the third monolayer is created here. So there is a pancake of, so outside here there is the height is 0. Inside here the height is 2. See, there are two monolayers here. The boundary are about the same. And then inside a third monolayer of height 3 units, 3 layers there. So it is 3 pancakes. And then so on. So what we are interested in is this place here. So how the fluctuations of our process, how our droplet behaves near this, near the wall. Okay, and then what we do is let us... Опять не работает. Ага. Okay. So, but to have just one layer, we don't even need to go to the three-dimensional Ising model. We can do the same just with a two-dimensional Ising model. So again, the definitions are here. This is now the same Ising model, but in dimension 2. And in this setting, we, instead of fixing the magnetization, this parameter M, we rather play with magnetic field H, which plays roughly the same role as fixing magnetization. So it favors plus phase or minus phase. So what is done here, we take a square box V. V is now the same V, but now it is a square box. And we have minus boundary conditions here. And to put extra pluses, we take this magnetic field with positive sign, and then it puts plus, it favors pluses inside our box. And again, we take beta to be large, it's low temperatures. And then the right scaling would be to put magnetic field to be of the order of 1/n, because the boundary has the influence of n. The length of this boundary of the square is of order n. The strength of the magnetic field is h times n square, and square is the area. So we want them to be on the same footing. So we want h and square to be of order of n, which makes h to be of order of 1/n. And this we studied that with Roberta Shlosman years ago, and the picture is the following. So when h is b/n with b small, we don't see any plus droplet inside our square box with negative boundary conditions. And when h is b/n with b bigger than some critical b critical, depending on temperature, then we have this picture of a droplet of pluses floating inside this square with the minus boundary condition. So this is the droplet in the box. That is how it would look like. So it's very much like the one pancake picture I showed you before. So this is the shape of the droplet, and here is the simulation of that same thing. So it's simulation of the two-dimensional Ising model with minus boundary conditions, which are yellow here, and with pluses, which are blue here. So this is this plus phase, and you see that that's how it is influenced by the boundary, the negative values of the boundary, and then we want to study the behavior of this random line in the vicinity of the boundary. And the answer to that is that this random line that goes to a diffusion process, which we studied in a long paper with late Dimayov, Sebastian Ont, and Ivan Velenik. And it appeared last year in the Annals of Probability. It turns out that this line here, properly scaled by the factor n to 1/3 vertically. So how should it's far from me. So we should scale this random line by a factor n to 1/3 this way and n to 2/3 that way. So this is the famous n to 1/3 scaling. After we do this scaling, this random line becomes a proper random process. It will become just a diffusion process, stationary diffusion process. So with this diffusion process lives in the positive half plane because it's above the wall. So it's this diffusion process, and it has a drift, and this drift is explicitly given by this function a of x is a logarithmic derivative of the function a capital, and this a capital is just scaled Airy function. So you take the Airy function, which is here, and then it has the first 0 at the point minus -1, and then you move the origin in such a way that this first 0 would be in the origin of your new coordinate system. This is the graph of the function a capital. So this a capital is what is this drift that we have in this diffusion process. So this is this diffusion in the in the upper half plane, and this diffusion process, well, it is positive because it is constrained to be positive, and it has the unique the stationary measure has density a squared, where I remind you that a is related to the shifted Airy function here. Okay, so that is, so to say, the end of the story about just one line.
So connect the diffusion process with the limit shape of the curve.
Well, it is not the whole limit shape. It is more than the limit shape. It is already fluctuations around the limit shape. So this is the limit shape. The limit shape is just a solution to variational problem.
Okay, understood.
Now you take this the line itself, and you want, okay, so this tells you about the law of large numbers. So this, yes, and now you want to know what is happening there at the boundary. So which is here. See here you see nothing, of course. You do the scaling, and then the fluctuations disappear. Now you want to know what are the fluctuations, and it turns out that what you should do is to scale by n to 1/3 this way and n to 2/3 that way, and then you get a proper random process. So this is namely you get the diffusion. And what is important about this function a of x? So this is the leading eigenfunction of the Sturm-Liouville operator, minus the second derivative plus x on the positive half line with 0 boundary condition at x0 at x equals 0. This is by now a known diffusion. It has its name. It is Ferrari-Szpon diffusion. It is called. So this diffusion process on a
May I ask some question?
Sorry?
Some question.
Sure.
You know that it's not only stationary but ergodic. This diffusion process.
This is correct.
How do you know? What are the reasons? How do you see it from the coefficient?
Well, you should do the spectral analysis of this operator, and then you know all the eigenfunctions and eigenvalues, and this is how you know it. So
Okay.
This operator has all the. I will say more about it. This operator has a discrete spectrum, and every eigenvalue has multiplicity 1. So that's the reason. Okay, so that's the end of the story with just one line, one pancake. But then we want to know what will happen if we have several of them, and this also can be done, and this was done well. And for that, just to give you the answer, what one has to do is to, as we saw, we need to know this the property of this operator, second derivative plus x minus second derivative plus x on the line, and now we should consider n-dimensional differential operator, sum of the second derivatives plus x1 plus x2 plus xn in n-dimensional space. And again, we need to study its eigenfunctions, eigenvalues, and so on. Okay, so let us ask so we know all the, by the way, we know all the eigenvalues of eigenfunctions of that operator. So I told you about one, this Airy function itself shifted to the very correct, very correct. When I will tell you everything, which is the following. So when you talk about just one line, one random line, you don't need 3D. You see that same phenomena in two-dimensional Ising model. Now, if you want to, but our initial question was about the three-dimensional case where you have several pancakes here, and if you look from the top, then you will see several lines. Well, this is the square, so we have several lines here in three-dimensional case, and we want to look into that window, and we want to know how those n lines behave. And you have n lines when you are in three-dimensional case, of course. In two-dimensional, you see just one single contour. But in three-dimensional Ising model, you have, on my picture, you have what, 4 lines. So there are 4 pancakes. They have boundaries, and those are 4 lines. And you want to know how these 4 lines are living together. This is what I'm talking about now. So the gap between lines is of order n or no, of order n to 1/3. Exactly. You don't know. You don't know what is huge and what is not huge, because right. Right. You thought I take it back. You totally Serежа, you are totally right. So let's go a little bit back to the pictures you are referring to. Here. So you're totally right. This distance here, as it is drawn, is of order n. This is true. What I'm talking about, n to 1/3, is those distances between other contours. Okay, so see, when you have three pancakes, then in some regime this distance is linear in n, and this one is cubic root of n. Okay, but see, also the same as here as well. So here is a distance of order n, and then it becomes a distance of order n to cubic root. And then I was not telling you the whole picture. So each pancake initially is at the linear distance, but it is not going on forever. When say you have already 20 pancakes, 20 in quotation mark, then you don't see this phase here. It immediately looks like this. So when starting from a certain pancake, this phenomenon disappears, and once the number of pancakes is large, then immediately they are like on that picture. So all the distances are of the order n to 1/3. It disappeared. So it's intermediate picture. So no, but so let me say it again. So when n is 3, the typical picture would be like this. For n4, maybe also like that. But starting from n25, the picture would be immediately, all of them would be immediately touching each other at a distance n to 1/3. Кто становится маленьким? Расстояние. Да, да. You see, maybe I was too fast and you didn't catch what I said. See, this is some value a. When you increase a little bit, what will happen is that the middle pancake would grow, the outside pancake would a bit shrink until they meet all together, and then they would coexist all together, and they will grow all together. And then it will happen a next jump, and the next pancake would appear. So for the first few ends, the next pancake, when it appears, it is smaller than all the rest. But starting from some n capital, you will not see this regime when the distance between the inner one and the rest is of order n. So depends on the size of your system or the temperature. It's some number. Sorry, no. The size, the value of the temperature. No. I take it back. Right. It depends on the temperature on your system. Yes, but it goes just fine. This picture is, in a sense, not typical. For few values of the extra magnetization, the picture looks like that for some intermediate A's, but then starting from some high enough value of this parameter A, you will not see, but you will see only the situation when all of them go together. So this top monolayer is never detached from the rest of them once the number of monolayers is big enough. Very good. So now I go to the conclusion, more or less, of my talk. So what I told you is that we have to talk about this operator in n-dimensional space, and we want to find its eigenfunctions and eigenvalues. Okay, seems very simple operator with some of those one-dimensional operators, but the question of eigenvalues depends in which region you want to find the eigenvalues of this operator with Dirichlet boundary conditions. So the eigenfunctions of the operator, Sturm-Liouville operator, I told you already, they are just the shifts of the Airy function to various zeros. You just have to shift the Airy function in such a way that the second, the third, the fourth zero becomes the origin, and this is the full family of eigenfunctions of your operator. And now, what are the eigenfunctions for this operator? As I told you, it depends on the box which you want to talk about. So the simplest box for us would be just the positive ortant, which for some reason, I'm tempted to call this the bosonic case for the following reason, that the eigenfunctions of this operator in the positive ortant are just products of eigenfunctions phi and I of xi. And the corresponding eigenfunction for this product would be just the sum of corresponding eigenvalues. So you just take a product of functions phi of different arguments, and the corresponding that would be evidently an eigenfunction for that operator, and the eigenvalue would be just the sum of those. What are other regions where you still can write down the eigenfunction? There is another case which is of interest to us. It is this Weil chamber. That's the region x1 less than or equal to x2 less than or equal to xn. So just such a wedge. In two-dimensional case, it would be just this region here. So you put again Dirichlet boundary condition, and then again one can write down, one can figure out what are the eigenfunctions of this operator in this other region. In that case, again, you can figure out what it is. What you should do, you should take now distinct eigenfunctions of the initial one-dimensional operator and make a Slater determinant out of those distinct eigenfunctions, and those Slater determinants would be eigenvalues of this operator, and the corresponding eigenfunction would be sum of corresponding distinct eigenvalues. So the operator is this one, the Slater determinant is this one. Is written here. You take functions phi I of xj, so I and j, j runs from 1 to n, and I is just index of the eigenfunction, and you take different phi i's, any collection of eigenfunctions phi i's, then you form this matrix, and then you take a determinant, and this determinant would be again the eigenfunction of your n-dimensional operator with in the Weil chamber with the Dirichlet boundary condition. Okay, and so now we have n points. They do again a diffusion in that in Rn in this wedge, and this n-dimensional diffusion process again has stationary distribution, and we should just take the first n eigenfunctions of our operator, of our Sturm-Liouville operator, and we form this determinant, and we square it, and this is the proportional to the stationary distribution of our n-dimensional diffusion process. Okay, and then this is, I believe, my last. Sure. On this slide. Okay, so what I'm saying, I'm telling you what are the eigenfunctions of this operator. You take n different indices NIs. NIs are NIs and I goes from the index I goes from 1 to n, n small, and then you take any collection of eigenfunctions but different. Those are NIs, and then you form the determinant. This determinant, and this is the eigenfunction. And okay, so now we have this formula for the distribution, and then we can take a limit as n goes to infinity and to study the top line. And this top line indeed becomes what is one can show. We did it with Patrick Ferrari. The paper appeared this year. So the top line converts to this ARI2 process. I will not tell you anything about it. And in particular, one can study the distribution of this line, and you can see that the 1-point distribution is what is called Tracy-Widom distribution. I told you nothing about it. So just the last thing I say, you take a large Hermitian random matrix, and you take the largest eigenvalue, lambda maximal, because your matrix is random, this is also a random matrix, and then you do proper asymptotic of this largest eigenvalue, and the distribution of that is given by this by now famous Tracy-Widom distribution. So that's it.
Thank you very much. Many thanks to Professor Shlosman for very interesting talk, for very nice presentation.
Thank you.
And we have more questions, please.
I have a stupid question from the very beginning. What was the array of spins you are discussing? Are they randomly oriented spins at nodes of real lattice or not?
Yes, they are random spins. They are random, and their distribution is given by the Gibbs distribution.
In real lattice.
In square lattice, in cubic lattice, right?
Well, diffusion is just propagation of the lattice order spins.
So
when you say about diffusion,
right, so there is an interface between pluses and minuses. This is now a random line, and I want to study the geometry of that random line, and this random line turns out to be a diffusion. That is. So the interface is where the spins are pluses and where the spins are minuses. Right. This random line, if you want to describe it properly, that in some cases this random line, if you scale it properly, the distribution you will get would be that of diffusion process.
Small question. One question. You say about KPZ scaling.
This is this 1/3. When you say 1/3, that is that you already can call it KPZ scaling. Though maybe Professor Hanin would object to that. He might say that there are different 1/3. Some are KPZ, some are not. But yes. When the scale, when you have a system of size n, and you see their fluctuations of not of the Gaussian order n to 1/2, but n to 1/3. This is what. Never heard. That's very interesting. Okay. Okay. So by now there are many cases where you see this 1/3. So it's, so to say, next generic feature. So it's Gaussian. There is a Gaussian scaling, and then with time you have more and more situations where you see this n to 1/3 scaling. Years ago, there was a conference in Paris called "Are all the 1/3 the same?" which I am happy, was very happy to be the organizer and the author of the title. But so 1/3 is really something, an emerging other next universal behavior.
You say it's n-dimensional space. It's n-dimensional.
No. ARI2 process is process of top line of the top layer. So the top, yes. You see this Tracy-Widom distribution for the top line. Yes.
And this distribution is the limit when the top line.
See those are matrices, but again, n is here as the size of the random matrix.
So if n is the limit.
You see limit there.
The same n for matrix. There are order of matrices. Yes.
This is formula for the order n, the Hermitian random matrices of size n by n.
The same n is the number of.
Right.